All right, we're about 1 minute late for Advent of Code today. I did do a stream today for Bevy, where we did this IK joint visualization, or joint constraint. So the cone is the constraint based on an angle, and the indigo dot here is where this joint should move to satisfy the constraint. The IK stuff is really coming along pretty nicely, so I'm pretty happy with it. But today is day 7. So let's pull in day 7 for Advent of Code and crack open day 7. Cephalopods, teleportation, magic smoke, tachyon manifolds. The error code, oh no. Okay, there's a diagram, that's our puzzle input. A beam enters the manifold at location marked S. Tachyon always moves downward. Tachyon beams pass freely through empty space. However, if a beam encounters a splitter, the beam is stopped. Instead, a new beam is fired from the immediate left and from the immediate right of the splitter. Wouldn't that imply... Oh, they always move straight down is the thing. Okay, gotcha. So the split is +1, -1 on the x-axis. Okay. Sounds like recursion. The beams kind of unify, so whatever kind of, I guess, data structure we would use, if it can account for us placing the same beam location multiple times, but only counting that once, that would be really nice. Process continues until all the beams reach a splitter or exit the manifold, so we need to keep like this box in play. To repair the teleporter, you need to first understand the beam splitting properties of the tachyon manifold. In this example, a tachyon beam is split 21 times. So actually, I think we only need the positions of all the splitters and the total height and width, I guess. My question here is actually for the splitters. This is a Christmas tree visualization, isn't it? It looks like for our input, which is kind of hard to show at that size. For our input, if we scroll down here, we end up with gaps on either side of every splitter. So the only thing we actually need to keep in mind is the height in this case, which is, I guess technically speaking, if S is 0, then this is the last line of splitters +1. But we can just use like the line count as the height here. We can completely ditch actually the horizontal because it doesn't matter because we'll never reach a place outside of the grid. So we never really actually need to care. Also, interesting things about the input is it doesn't look like you can actually end up in a situation where a beam would land on a splitter. So we never actually need to worry about that, which is cool. So this is basically going to be like start at 0. In our first loop, we go down 1. In our second loop, we check to see if any of the current positions have splits. If they do, then we don't count that, do we? Do we count the number of beams here? The number of times it's split? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So it misses one, misses this one. So we actually only need to care about the times that we hit the beam, or rather hit a splitter. So we can keep all the splitter positions in a hash map or something, or a B-tree map or something like that. We can keep the positions here either as a tuple or an IVEC from GLAM. We need a loop running here where the loop really only needs to know what the current horizontal level is, right? Because if we are here, then we have a horizontal level of 1. If we're here, we have a horizontal level of 1. If we're here, we have a horizontal level of 2. So it just loops over these, drops down, probably produces a new vec. So we produce a new vec for every line here. We haven't seen part 2, so I don't want to optimize too much in the sense that like try to reuse the same vec or, you know, something like that. So I think we'll just iter and collect. We could iter n times and keep a fold, right? Because we know that we're going to iter height number of times no matter what. And then we wouldn't ever need to actually check below the last line. Like we never need to worry about keeping the height around because we'll start with this and we'll keep going down until the fold stops here. And then the state that we keep in the fold would be the current horizontal line of vex that we have. So I guess technically, actually, we can iterate over these lines even. And we don't really even need to store positions per se. We only really need to store X locations. So I think what I'm going to do here actually is take this input, do an input.lines. The lines is the same number of iterators as we need, or the same number of iterations, sorry, as we need. We'll iterate over each of these lines as they come in, and we'll try to fold with the previous state, which is going to be a vec of X positions, and probably also the splitters that we hit. So we need the previous X positions, and we need the splitters that we've hit. Those are 2 vecs. I guess the splitters that we hit could be a hash set or something, but so that's probably what I'll start with. I'll probably start with a hash set. Hashing, in this case, there's not all that much going on, so while hashing, generally speaking, is slow for Advent of Code, I'm more interested in getting like a semantic read on what is supposed to happen here. So I think that's what we're going to do. The approach here actually doesn't even need a parser. I guess we could write something that gave us back a list of all of the X positions, right? Just the enumerates and the X's. But we could do that inline too. So let's get started here with a input.lines .iter. Well, we don't need a .iter on lines. Input.lines. And then I think this is going to turn into a fold. This fold is going to start with a vec and a hash set. And this is going to be positions and splitters. I've got my syntax incorrect here. We need to bring hash set in. What is wrong with fold? Let's do cargo test p day 7, part 1. Expected result string report found unit. Right, because basically the result here is going to be we don't care about this, and the hash set is going to be here, and this is going to be set.length.toString. Okay, so this should be our whole deal. And then the issue here is that we haven't actually done anything in here. So if I did something like this, oh, this is multiple arguments. This isn't a tuple. That's why. And this is actually what I wanted, because the next line is going to come in there. And this is going to be a vec of something, and we could actually put the types up here. And then we actually don't need to type them here. We can just initialize them because the type is being inferred from the return type, which fold gives us. So we end up with positions and splitters over each line. In this case, we're just returning all those positions and splitters. So let's get like splitters in here. I guess a line, right? So this should log it out. And we need to get our test log test. We'll skip the input. And we end up with a fold that gives us every line in order. Some of these don't have anything, no splitters in them, which is interesting. I don't know. I don't think it'll be an optimization to do like a dot contains splitters or something like that. But so we have splitters and positions, and we have our next line. I do feel like we could do something a little bit easy for the setup, right? S position equals input dot. Well, this is going to be wrong. Let's do let line iter equals this. Let's do a mute line iter. Let's do S position is line iter dot next dot unwrap dot position val equals dot position. No, line iter next unwrap position S, and then this is the line iter dot fold. So this will be everything else basically, and then positions here will include S position, and this needs to be brought down. This is not a function. This is not an iterator, right? Cars position, whatever. And then we can unwrap this. And I'm just going to cast this to U32 because I know we don't have anything there. So we end up with starting with a first line, but we start with our S position here. I guess technically also we could check for like S or splitter or something like that, but yeah. So I guess positions isn't really a vec either, because positions needs to, how do I say this? Positions needs to be unique, right? So we end up with positions and splitters. And I guess we could enumerate here, right? Line iter, let's see, line iter enumerate, right? Dot one dot cars, and then this line ends up being y index and line. So we really need to positions dot iter. So if we iter over this and we check the index, which is the directly bottom part, and we do, I think I want to write this in a slightly different way. The splitters, I kind of want to be in XY position. And I'm finding myself writing like as usize quite a bit. So I think we're just going to use usize here. And positions is going to be that hash set, right? Because basically we're working with a bunch of indices. And indices are basically always usizes. Especially when you get them from like Rust standard library functions. So there's that. We're going to fold here. We're going to have our positions for all of our X positions. We need to iterate over those and check basically the next line to see if it has a splitter in that location. If it does have a splitter in that location, then we actually need to push into splitters. So for that reason, I'm going to do for position, or rather for index in positions, I think, rather than collecting this for any reason. And string slices implement a trait that allows you to slice into them, but not a trait that allows you to index into them directly. So there's slice index is the name there. Let's see, Rust slice, right? So slice index is indexing by slices. There should be, if we look for index, index is implemented where slice index is implemented, but not more generally. So if we split, then we need to, why is insert not auto-completing there? Insert auto-completes here, but not if I type in. Perfect. Wonderful. Right, so our new positions is that split index, +1, -1. Otherwise, new positions is just index. And then splitters needs to get added to here, right? If we're splitting, we store the splitter location. So this is splitters.insert. What is going on with my autocomplete today? I don't know what's going on. And I made this a tuple, so this is going to be XY, and this is new positions and splitters. And we run our test here, and we end up with nothing because I didn't put the right value in our test, which is 21, which is what we're getting out of our equation here. So now our test is passing for realsies. And let's try to run it and make sure it works. Day 7, part 1, we get 1504. Submit. That is the right answer. Perfect. Okay, before we take a look at part 2, which I'm sure is wild, we've got our process function. So first of all, our input looks like this, right? There's an S at the top and a series of splitters. We kind of want to start with this value having been processed. So that's what I do here to grab that position. I could probably clean this up a little bit. I do all of my operations on string slices in Advent of Code, but there are plenty of people who do them on byte slices, which is totally valid. And actually for Advent of Code ends up in faster solutions. And also lets you do direct indexing. So if you use byte slices, because of the way that Advent of Code tends to be set up with only ASCII characters and expecting you to be able to index into things like strings, U8s can be better, but I still like using string slices for whatever reason. So the return value from this line iter, we've chopped the first line off, which is that S line, and initialized our S position. We start off our fold for all of the rest of the lines with that S position. Remember, we enumerated when we called lines, so we have the index for everything moving forward. That is the correct index on the y-axis. We have our hash set of positions and our hash set of splitters. We fold over this, which gives us a line each time it iterates, as well as the y-index because we enumerated. In this case, we just take positions and iterate over it, take ownership, iterate, and we create a new positions hash set. Technically speaking, I guess we could mutate this one instead of creating a new one, but, you know, it's always good to not over-optimize part ones. So we get our new positions hash set for every index, which is actually one of the benefits of doing it in the way that we're doing it. We get to only care about the X index here. We don't have to do like a hash set for an IVEC or anything like that. We just do for index in those positions, which is the last positions. If our line at that position has the splitter, then we split. If we split, we take the left and right split positions and throw them into our hash set. We also throw the total position and the grid of the splitter into our hash set. Otherwise, we just continue going downward in that index, and that's the whole problem. So I'm expecting, once again, to kind of like have performance issues with hash sets. So this is 400 microseconds. Again, not particularly fast for what we're doing. We are using a lot of hash sets. We could use a faster hasher. We covered that. I think I actually have Rust-C hash installed, so maybe we just .workspace equals true, right? And then part 1, instead of having hash set, we use Rust-C hash fx hash set. And all of these hash sets get an fx on the front, and I need to make sure that I don't double that up. And no function new in the hash set, huh? We're going to switch to defaults, I guess. Also interesting that this doesn't allow us to build a from. This is like entirely not a problem because we can do like a default set and then insert this. And my question here is what's going on? Argument has type usize 1. Oh, right, because we have an array here. So we just throw this into a block, do our initialization, and then return that value as our initial value. So even if there is no new, even if there is no perfect like function to just pull in this array, which I don't know why there isn't on fx hash set, if I'm being honest. Like I feel somewhat confused as to why there wasn't a new function here. I think that might have just been because I guess there is no new, which is interesting. I wonder if new got added after fx hash set got published. Feels weird. Anyway, now our bench drops from 400 to 165 microseconds, and just make sure that it actually is producing the right solution. So 1504. So, hashing is not particularly performant, and using a correct or a faster hasher can greatly improve the runtime of something if you don't have the security concerns of the default hasher. So I'm going to leave fx hash set in here because there's no downsides. And we'll move on to part 2. So with our analysis complete, quantum tachyon manifolds, only a single tachyon particle is sent through the manifold. A tachyon particle takes both left and right path. It's time itself that splits. What you really need to know is the number of timelines active after a single particle completes all its possible journeys. What does that mean? In this example, in total, the particle ends up on 40 different timelines, so it's just hold more state, I guess, because every time this splits, it creates a new quote-unquote timeline. So instead of using fx hash set for splitters, I think that we forever grow the positions. So we actually don't need to track the splitters, and positions just grows forever and doesn't actually need to be a hash set because we're going to grow it forever, right? So this can just be a vec, because if we're not concerned about removing duplicates, then this is just a vec, right? Splitters then doesn't exist, new positions does. So we just want to keep track of all of the positions, and we split if we split, and we don't split if we don't. And this needs to just be a vec, and these can all be push. We don't need to track the y-index anymore, right? So we'll just remove a bunch of processing, basically. And I just realized I did this all in part 1. Oh, hang on. Let me back this out. Oh, no. Okay, let me back this out to the point at which we implemented fx hash set, and then we will copy this file, I think. Okay, let me make sure that part 1 actually runs and does the right thing. Perfect. Part 2. This is part 2. Now we're in part 2. Our answer for part 2 needs to be 40. Oop, that's not what I want to do. Cargo test part 2. Test part 2 passes. I assume that for some reason this runtime is going to be huge, but I can't imagine it being that big. Like the input here just is not big enough in my mind for the iteration that we're doing, right? We've got 142 lines. And the iteration that we're doing is just a couple of pushes per line. So unless I've really messed something up, I feel like this should stop. We quite literally can't be in an infinite loop because we have a fold. So I know that I took away the enumerate here, but maybe we throw enumerate back in, and here's lines, right? We log index and positions.length. Rust log info. Let's get rid of these split apps. That looks really weird. Hang on. So we'll rust log info, run in release mode. That's why. So we end up at index 100 pretty quickly, but we kind of stall around then. This is growing to be quite a bit of numbers, which is quite a bit of allocation, which explains entirely why it's slow. We need to get to 141, and we are at 107. So it's starting to feel like the way that I wrote this is kind of not going to complete. So really the answer here is going to be tracking the number of each of the beams in each of the locations to speed this up, right? So we don't actually need to keep a vec of all the positions. We can keep a vec of the positions of the beams and how many beams are there, which is not a vec. So if it's not going to be a vec, it's going to be a hash map. I think it's going to be fine. And it's going to be a hash map of what, U size to U size, basically. And we kick it off with S position 1, right? So hash map view size to U size from this array. This is now positions. Positions is also going to be this. I'm just letting this run on the side because I think it's fun. I actually don't anticipate that will even finish by the time we fix this problem. So new positions is new size, U size, and then if we have a beam split, then this is not insert. This is going to be like new positions. Actually, let's figure out why this is all red. I'm going to keep running. I'm going to keep running that. Let's see. Unclosed delimiter, of course. Where is our unclosed delimiter? Here's our for loop. Here's our fold closure. Here's our fold. Hang on. I missed a paren here. So let's pull in hash map. Same thing. We could probably upgrade this to FX hash map later. Line as bytes index. This is going to be what index count is what I'm storing this as, I hope. It's nice to use new types here or type aliases. So like, right, count and position, which are both just going to be U sizes. And then this is basically documentation, right? And this is going to be position and count. And now every time we construct this, we kind of can get a view into, oh, right, what did I put in which place? Even though, because they're the same type, right? So we have index and count. And at the index, we have some count. If we're going to split, okay, so I shouldn't have let this run. But I think what's interesting here is basically that because I let this run, it used up all of the space my computer had and OBS crashed. So just to give you kind of like an insight into whether this would actually finish or not, it doesn't. And it doesn't because of space constraints specifically. So hopefully I didn't lose any of the recording, but we'll find out, I guess. I record in formats that should survive the event that just happened. Closing delimiter, possibly meant for this. Cargo test, whatever. We're getting nothing. So we are in the position of, we are folding over this. We have new positions. New positions, dot entry, index, or insert. I think it's end modify or insert. I kind of always forget the order here. The API that I'm using here is the entry API. So if you call dot entry with a key, a typical pattern is to do end modify or insert. End modify gives you access to the value if it exists, and or insert inserts if that entry is empty. So you typically see end modify combined with or insert. So this is end modify count, and this is going to be index -1 and index +1, right? So we do index -1. We're not going to return a value here. I named this the same thing, which is a terrible idea. Value plus equals count, right? And this is also going to be the same thing below, but we're going to do an or insert as well for count. Same thing below for the +1 position. So this is going to be +1. We're going to add this or insert here. So this is basically the same thing, but instead of keeping all of the indexes, we are going to keep a count of all of the beams at a particular index. Same thing here. We want to do entry and modify or insert, and we want to do this for the regular index. So we end up with this set, which is now a map, right? And this gives us, right now, all of the, so we do set.values.sum U64 toString. And this is map because I just renamed it. And U64 is an issue for some reason. I guess usize, right? Map values sum, right? I guess we used usize for every, wow, I cannot type right now. I guess we used usize for everything. So if we run part 2 now, we do get a passing test for part 2. If we run in release mode, we basically get an immediate end to our program. So the gold star is ours, huzzah. So part 7, basically the insight here is that if you're going to have this many things to track, don't just keep them around, but keep them alongside a count. So cargo bench day 7, this should end up as significantly faster than. So we end up with like 160 microseconds for part 1 and 243 for part 2. And even though I had it already in the file, I didn't use fxhashmap, which of course for some reason doesn't implement from, which is so weird to me, right? So we end up with what we wanted, and this is just default. It would be really nice if that, let's get a cargo run here to make sure that we have the same value. This looks like the same value to me. I didn't really check, but yes, it is. So now if we bench for part 2, we end up with 135 microseconds, which is even faster than part 1. And most of our time is going to this hashing. So functionally the same solution as part 1, except for the fact that instead of keeping all of the values, we are keeping just the counts of the values, which greatly reduces the amount of space we need, which greatly reduces the amount of allocations we need, and so on and so forth. So I think that's it for today. Key takeaways: keep track of the count, not all of the individual values, and FX hash or alternate hashing algorithms are faster than the default built-in ones. They're also less secure, so important to remember that. But for Advent of Code, use a fast one. And that's it for today. I will see you tomorrow for day 8.